Hello, welcome to Chapter 11 of Geology for Gilbert Community College. In this chapter, we're going to cover crustal deformation and mountain building. I say crustal deformation, and what I mean by that is deforming or changing of the crust. Again, I'm not talking specifically of individual rocks, but more so the crust in general, the plates, the tectonic plates we've been talking about. So, what can cause a rock or crust, in this example, to deform? The answer, of course, being stress. You push, pull, do something, add a force to a rock, eventually that causes the force to deform. When stresses on a rock exceed the rock's strengths, rock deforms by folding, fracturing, and faulting. We'll go over each of those individually as we go through. And the magnitude of this stress is a function of the amount of force applied in a given area. Pressure. You learned about that in physics class. Pressure is the way force relates to area. So the amount of pressure and how strong the rock is, both are aspects that affect its deformation. We say deformation and we mean all the changes in the shape or position of the rock in response to some stress or applied force. In geologic terms, we refer to the structures that are caused by this deformation, including folds, faults, and joints. And again, we'll get into all those as we go further. So let's take a quick second and let's look at this geology here. Let's look at this picture. What do you see? What do you think originally happened to this rock, to this geology, to create what we are seeing now? Remember, the concept of superposition, the idea that all the rocks that when they originally were laid or originally were deposited, laid flat. Rocks don't deposit in weird designs like this. So this rock was originally flat. Something happened to it, some force, some push-pull happened to it to deform it to creating these unique shapes. Try to take a second, trace out where these shapes appear, and try to get a good idea of where a fold or a fault occurred. I know we haven't discussed folding and faulting yet, but you know what faults are from our previous conversations of earthquakes, and folds are exactly what they sound like, a folding of something. So, you took a few seconds, hopefully you paused the video to take a good look at it. Now let's look at this sketch detailing what's going on. Notice here, the sketch outlines a syncline, an anticline, a fold, and a fault. These we're going to go deeper into as usual, but the important thing to catch here is the geologist's sketch outlined the color, the white band of strata, the white band of geology, and it defined certain key points based on that white band. Take a few seconds, go back to the original image, and trace that white band if you can. You will notice where the geologist's sketch has a fault zone, that is where the white band itself disconnects. When force happens on a rock, we term that process strain, or the change in shape of the rock caused by some sort of force or stress. A strained rock loses the original shape during deformation. And sometimes science uses weird nonsense words to describe what happens. In this case, the structural geologists use very simple words. You apply a force, you apply a stress to a rock, it strains it, it bends it, it breaks it. Or doesn't break it. We'll get into that. Technically, when you deform a rock, it undergoes pressure, as we've been saying a lot. Pressure is the way force relates to area. There's two different types of pressures. Two different types of stresses. A confining pressure is a stress applied uniformly in all directions. When you bury a rock, it undergoes more or less a confining pressure. Metamorphism is partly the result of confining pressures. Differential stress is, when the pressure is not even throughout the rock. For example, if we look at these pictures here, a cube of rock, undeformed rock, may be under some sort of confining pressure, may not be. But the fact that no strain has occurred within the rock means no strain has occurred within the rock. It's not changed. B, we have a compression, a shortening effect happening in the rock, where the majority of the pressure is coming from the sides, left and right sides, pushing in. C, tension, is a pulling out of the rock on the left and right sides, stretching the rock out, as we can see what happens. And then D, that cartoon D, shows a shear stress, where a combination of B and C to tear or slide the rock apart. These are different things you can do to rock, and of course, all these examples could be different angles, could be different amounts, not always equal. But this basic concept of push, pull, or push and pull define the different ways that a rock can deform due to differential stress. And here we zoom in a bit. Compressional stress squeezes and shortens the rock body. Take a water bottle, push it, what happens? The water goes shooting out the top, right? Compressional stress. Tensional stress pulls apart the rock and lengthens it. This is shown in these images as push and pulls because that's a good physics description of it, but it's not always necessarily a push, just simply a push or a pull. You can have tension from different manners. The world's ridiculous. The way these things actually work in the real world is very, very vast, so that's why it's compartmentalized into these few stress types for each of your description. And as we talked about before, this final zoom in is on shear stress, or stress that is applied in opposite directions. A push from one, a pull from another, for example, where things are not simply uniform across one dimension. The deck of cards is usually a common example of this. When you push a deck of cards, a cube turns into some sort of rhombus or diamond shaped, right? So we're pushing rocks, pulling rocks, we're applying forces, applying pressure to rocks. What can happen to the rock? Two responses are available, a brittle and a ductile response. A brittle deformation happens when the rock breaks, because the rock is brittle and it, breaks, right? A ductile deformation, as opposed to breaking, is a bending or a changing of the rock. And within that ductile category, we have subcategories of elastic and plastic deformation. Elastic deformation happens when the rock returns to its original size and shape when the stress is removed. Plastic is where the rock is changed in some way. And funny enough, these two are related to each other because once the elastic limit or strength of a rock is surpassed, then it either bends or breaks. So 2A is more of a precursor step, and then 1 and 2B are the two results if you get past 2A. So the organization of this list is correct, and it's questionable at the same time. But hopefully you understand the idea. In order for you to bend something, you need to put enough pressure on it to bend it, and then if it bends or shatters depends on, what's bending or shattering. And outside circumstances, of course, play a factor. Some of these factors can include temperature, and other factors can include pressure. We've talked about temperature and pressure a lot as it refers to rocks, with igneous, with metamorphic, technically with sedimentary if you want to get specific about it. The higher the temperature a rock, the more chance it has for a ductile deformation. Cooler rocks become more brittle, and then as you squeeze rocks, you make them stronger and harder to break. Rock type, of course, plays a factor into this. If you have crystalline igneous rocks, for example, are very brittle, tend not to want to bend and distort, whereas sedimentary rocks and some low-grade metamorphics actually more readily undergo ductile deformation. The biggest factor, the thing that people always forget when this conversation, is time. Yes, any rock's going to break before it bends in a laboratory setting in the space of a human lifetime. But if you apply a force over a geologic scale of time, we're talking tens of millions, hundreds of millions of years if you want, you will get ductile deformation as opposed to brittle deformation. A good example of this would be, they use train in this example, but you go to an amusement park, you can put a penny in a machine, and it will bend the penny and stamp it in a new way. This bending of what you would usually consider solid, strong material like a metal coin is an example of ductile deformation. Something happened, pressures happen to the metal, and the pressures happen at the correct speed, at the correct temperature, at the correct pressure, etc., to allow the usually hard, not flexible material to bend without breaking. We've talked about the types of pressures that can go on a rock. We've talked about the type of things that cause rocks to deform. What actual deformations happen? First, I want to talk about a fold. A fold is, well, what it sounds like, where the rock appears to fold up like a deck of cards or a piece of paper. In this example, we have some sort of geologic strata stacked up. Pressure comes in at the long ends and it folds it up. A result is a shortening and thickening of the crust as shown here. If you look, the top parts of the crust at the top of that fold are a little thinner, and the crust at the ends is a little thicker because of this folding material. Again, think of a deck of cards. When you shuffle a deck of cards, you do what's that pyramid fold or whatever it's called. What happens? The cards in the center are all squished together a lot. The cards outside are fanned out more. They're thicker at the sides, thinner at the top. This happens with rocks as well. When you do this to a rock, at the end of the folding, you end up with what's called an anticline. An anticline is when a fold is arched upward in the center, and the oldest strata are in the center. As shown in this picture here, you had some flat material that was folded up, pinched up where the top is arched up, and then you essentially form a hill. What happens with a hill? You're going to have erosion happening. The top of this hill eventually is going to be eroded out flat, leaving you with what's shown here after erosion at the bottom. The center of this anticline actually digs into the older rock. You see that yellowish looking rock, that center that is older than the rest because it's lower down in the strata. That is appearing at the axial plane, and then the younger rock, this grays and this upper layer of yellow, don't actually show up in the center of this anticline because they've been eroded away. They show up on the periphery and the outside of the anticline, but not the actual axial plane or the, well, hinge line, as shown here. And a good way to remember this, anticlines, the A points up, anticlines point up. And here we have some classic examples of anticlines. Notice here, if you follow the color of the strata, you will see it making this upward facing arch. It looks like the top of the A. That is an anticline. Here we have a road crop, and again, follow the colors of the strata. You will see them bulge up and then swoop down, making, again, the top of an A fold that's been pressed along. You can look at this, and you can imagine, picture where the force was coming from relative to this rock, right? It's coming from the left and the right of the picture to create this anticline. And this last picture is really interesting. It's an overturned anticline. Again, this was kind enough, the geologists here were kind enough to provide these dotted lines showing the folding, showing the strata. What happened was this anticline, this fold happened, and then something literally shoved the anticline over to the side, giving you something that's been overturned. So the original top layer is that outside-most dotted line. That all is the youngest strata, and the oldest strata is on the inside dotted line in the center going to the bottom left. If a fold bends up, we call it an anticline. If a fold bends down, we call it a syncline. Good to remember, it's got a Y. The Y is shooting down, syncline. These are troughs of rock layers where the rock sinks in the center, providing the youngest strata, actually, on the center of the rock. As with the anticlines, follow the colored strata. You can see it dipping down in that syncline fashion. There you go. How did this get that way? Well, try to picture the geology. Try to picture a set of circumstances that would cause this rock to deform in this fashion. And if we consider at one point all these strata were vertical, were laying on top of one another with the younger strata on top, where's the younger strata in this picture? In the center of that bowl, that white and that black strata up there in the center, in the center of the syncline. Exactly. Here is an example with a person in it for scale. This large, very tall rock layer, this very tall stack of strata, was all deformed in such a way to cause this syncline to form. Something, again, to keep in mind as well, we have all these cute little cartoons and images of this pressure. In the real world, pressure isn't just along one particular axis. Pressure comes at many different angles, many different sizes, many different rocks, many different heats, temperatures, pressures, etc., etc., etc. So this cartoon here shows you the theoretical symmetrical fold, which doesn't really happen, and then your asymmetrical and overturned folds, depending on the pressures, how they show up, what happens when they happen. The overturned fold, again, is a very interesting, unique sign. As you can see there, I think it's usually shown as limestone. That brick-like structure actually is folding over top of itself, so much so that the axial plane is passing the 45-degree line. We talked anticlines, we talked synclines, now let's talk domes and basins. Domes and basins are, again, what you think of when you say dome or basin. A dome is an upwarping, producing a geologic feature where the older strata is in the center, and then in circles outside of it are the younger strata. A basin is a downward warping where the youngest strata is in the center, and then circling out from it is the older strata. The words describe exactly what's going on. There's no fancy science speak here. Here is a diagram, a cartoon of the Black Hills of South Dakota, and if we notice, Mount Rushmore is sitting in a granite section that is enveloped by some schist, which is then enveloped by a limestone. How can you get this circular pattern? Well, if we go down to the cross section at the bottom of the image, we see that we have some sort of dome-like structure, right? An upwelling of the granite through it, deforming the schist, the limestone, what have you, surrounding it. A dome. You may not realize that the underlying structure of Mount Rushmore in the Black Hills is in fact this dome structure, but a good study of the surrounding geology, good mapping of what's there, provides this information. Lower Michigan is in fact actually a basin. It's not a basin in terms of topography, rather it's a basin in terms of the rocks that are present, where you have this circular motion with the younger strata just a little bit in the center there, around where that'd be Mount Pleasant, I'd say, and then expanding out more and more and more in this, again, circular fashion, older and older and older rock. So much so that Michigan itself is actually surrounded by Silurian, very old aged rock and all parts of it. But Lower Michigan itself, the entirety of the geology of Lower Michigan is younger than all the geology that surrounds it on a state-sized scale. We gotta end our conversation of this incredible folding technique with the most boring fold there is, the monocline. A step-like fold, otherwise horizontal segment, where something bumps up a little bit. We talked ductile deformation. Let's do some brittle deformation. Joints would be an example of brittle deformation. These are fractures within a rock where there was not any displacement necessarily. The rocks themselves do not move in relation to one another. In fact, due to the stress, due to the force of whatever's pushing this rock, they just snapped, cracked, giving you what we call joints. The more common known brittle deformation is the fault, which is a fracture in the rocks that occurs along with the displacement of the rock. Sudden movements along faults are in fact the cause of most earthquakes, as we talked about in the previous chapter. Within faults, there are many different varieties. The first one we'll talk about is the dip-slip fault, or movement that is parallel to the inclination of the fault plane. Within a fault of some sort, you need to have some terminology. We're going to have two terms here, a hanging wall and a footwall. Hanging wall, as the picture will show in a bit, is rock above a fault. Footwall is rock below a fault. So once you know the termination of the fault, you can describe its movement based on hanging walls and footwalls. And here we have our image. Notice where the fault line sits. According to the angle of that fault, the hanging wall, the hanging block, will be what's on top, and the footwall block will be down below. We have a picture here of a fault zone with an up fault, the rocks pushed up on the left here, and then a down fault, the rocks pushed down on the right. And the fault scarp, the separation point where actually the upfaulting went up, that is what the person is standing on. So let's talk fault types. In dip-slip faults, we will first discuss the normal fault, where the hanging wall moves down relative to the footwall. This is associated with tensions as the rocks are pulled apart and can form at divergent plate boundaries. Again, we need to look at the angle of the fault, and whatever side is on top, we call the hanging wall. So if we look at the graphic, the cartoon on the top here, the wall that was sitting on top fell down. That's the hanging wall. The hanging wall fell down. So we call this a normal fault. And then after some erosion, we can see that the footwall has the elevation to it, and then the hanging wall is where you get your water because, what happens with erosion? Things go down with gravity. The hanging wall section was what was eroded down. This picture is very stark and does a very good job of explaining all of these ideas. You can very clearly see the fault line in the center of the picture, right above the person's head. You can tell which one's the hanging wall because it is on top of that angle, and you could tell that it fell compared to the footwall because the footwall has that very nice blue-gray strata in the center that is of a higher level. Here again we have two more faulting, lots of fault zones going on, and you can see that red strata in the center pushing up and down as these cracks and wedges go throughout the rock. If you have the reverse of a normal fault, that in which the hanging wall moves up relative to the footwall, you have a reverse fault. How surprising. These are associated mostly with compressional stress as the crust shortens, and you can kind of picture if you're pushing in on the compress, something's going to ride on top, right? Lastly, we have thrust faults. These are low-angle reverse faults formed by lots of compression, and the most pronounced among the convergent plate boundaries. And we'll go into the graphics so it gets a better understanding of this, but this all always boils back down to what it's going to look like. You can do all of these fault types with a deck of cards and see exactly how they're going to work in the way they work. This graphic should look familiar, except that the fault orientation has been switched so that the hanging wall is on top and the footwall is what follows. Same basic rules of erosion happen as with the previous graphic. The thrust fault follows these basic ideas of the compression, except a very stupidly low angle of faulting occurs. The hanging wall here is pushed up so much so that you can see the red strata, the red geologic section, is on top of, everything. As with previous, if you have a layer that both has an obvious fault line and a very well-defined strata, different color, like in this example, the red at the bottom, you can see these thrust fault zones very well described. And you can picture what's going on here. Again, take a deck of cards, shove it together, this very stuff happens. Here we have a picture describing these two examples. Take a second, pause here, look, can you tell which one is the normal and which one is the reversed fault? And then finally we have another example here, again, showing high angle faults, showing beds, layers that very well define which went up and which went down in accordance, things of that nature. Again, when you're going out in the world, when you're walking around, take a half second, look at a rock wall, look at some geology, and you will determine that there is millions of years of history in what you're staring at. It's quite fascinating, and thanks to this class, you can understand what's going on a little bit better. You're welcome. Those dip-slip faults were of course very interesting, but we also have strike-slip faults. We talked about this in previous chapters already. We'll go a bit better into this here. A strike-slip fault is horizontal displacement as opposed to vertical with a dip-slip fault, and is parallel to the line of the fault. At this point, you have a right lateral and left lateral facing strike-slip fault, which is described by, as you face the fault, the opposite side is moving either right or left of you. Naturally, we'll use the San Andreas fault to describe this. So, stand on one side of the fault, look at the other side. Did it move to the left or to the right of me? And I understand there's an obvious issue here, which, what side of the fault do I stand on? Yeah, that's a problem, right? That being said, if you understand from a larger scale term what the faults are doing, you can have an understanding of if this thing is moved left or right accordingly. So this geology is both local geology and regional geology combined together to understand how these systems interact. If a strike-slip fault is large enough, we call it a transform fault because it literally transforms the nature of the planet. San Andreas fault would be a transform fault. It's also a strike-slip fault. Same thing, just transform is the large scale, the plate tectonics version, whereas strike-slip can be a local faulting event. We've talked about plate tectonics and their motion. We've talked about deformation and faulting. Now we can get into orogenesis, or the formation of mountains. The world itself is covered with a vast variety of different mountain types. Here we have in red, young mountain belts, less than 100 million years old. In blue, old mountain belts, which would by definition be greater than 100 million years old. Shields, which we've discussed previously. And then stable platforms, which are shields that are covered by sedimentary rock. Why do some mountains exist as red and some as blue? Why are some mountains old, some are new? Is there any association with the plate tectonics surrounding what's going on? Why the shields exist where they exist, etc.? Let's discuss that. What types of mountain building do we have? The first type we'll discuss is the island arc mountain building, the island arc orogenetic events. These are the result of subduction from oceanic lithosphere and form at ocean-ocean collision events. They contain lots of volcanic rocks, some metamorphic rocks, and are defined best by the Aleutian Islands in Alaska. We'll be coming to pictures like this a lot. If you look at find Alaska in the upper left, the Aleutian Islands, to remind you, are that little extension coming around the bottom of Alaska. The Alaska Range is part of this section. We've covered the Aleutian Islands before, and we talked about plate tectonics and ocean-to-ocean collision, so this should sort of be old hat material to you. But if you picture the ocean-to-ocean collision, you know that just take a piece of paper, push it on both ends, it's going to pop up. This pop-up occurs, builds these mountains, builds these volcanoes, builds the Aleutian Island chain. If you don't have ocean-ocean collision, you can have ocean-to-continent collision. These collisions build Andean-type mountains, where the oceanic lithosphere is subducted beneath the continental lithosphere. The Andes Mountains, namesake, the Cascades, and the Sierra Nevadas are all examples of this. The Andes Mountains, of course, cut along the western side of South America. Notice on the eastern side of South America is the Brazilian Shield. Not a mountain range. There's highland, sure, but very much not mountain. Why is that? Think back to the plate tectonics conversations we had closer to the beginning of the semester. You should understand why. You've seen this cartoon already. We talked about this when we talked about igneous rocks, talked about this when we talked about plate tectonics. We're looking at it again, but this time we're focusing on the mountain building. Plutons pushing up the continental crust, forming mountains. This is how the Andean-type mountains are formed with that collision of oceanic and continental plates. When a mountain chain is formed in this method, you tend to get a thicker continental crust, again because the Pluton is upwelling within the crust, many volcanic rocks, many intrusive igneous rocks, again, from this Pluton forming, if we think back to our igneous geology lessons, some metamorphics, and lots of folds and reverse faults. And look back at the previous image, think about why would all these things happen? It makes sense. Here we have some images from the Andes Mountains. Here we have some in Chile. And noteworthy here is that they don't really look all that different from other mountain ranges you've seen. This sort of mountain building is more to do with the large-scale macroscopic what's going on with the plates, more so than the individual mountains are going to have a particular look to them. Of course, Machu Picchu is in the Andes Mountains, very famous place to visit. Here's some more mountains. Again, these mountains don't look different. If I showed you this picture, didn't tell you where it was from, you wouldn't be able to necessarily tell me what type of mountain range building, what or genetic event took place here. That being said, this is a Andean type mountain range. And if we look at the U.S., the Cascades and the Sierra Nevada, there on California, Washington, Oregon range, are built in this fashion. Why? Because the Pacific plate is subducting underneath the plates of the United States, creating this type of mountain. Within the U.S., we still have here Mount Rainier, a Andean-type mountain in the Cascade Range. The Sierra Nevadas, of course, I said already, Mount Whitney. These are mountains that look no different from any other mountain range, but, as I said previous, Lake Tahoe, Sierra Nevadas, the geology tells you a lot about how these were formed and how they differ from other mountain ranges. We covered ocean, we covered ocean-continent. Now we can talk continent. Cordilleran-type mountain buildings. These are formed, again, via microcontinent collisions, and they form because both plates contain buoyant continental rock, so minimum subduction occurs, right? You get your igneous, metamorphic, and sedimentary rocks here, and lots of folding and thrusting. Since you're slamming two of the same type of plate together, you don't get that buckling down. You get a different event. Still produces mountains, but you have different side products and different results from it. Notice here from A to B to C to D, we have this microcontinent and this inland inactive island arc coming in towards the continent. At some point, the subduction stops because that microcontinent's not going to go underneath. It's buoyant. It's instead going to collide in with the standing continent, and this collision itself produces a mountain range. We're fortunate to have the west coast of the United States of North America, I should say, the west coast of North America be a good example of all these different types of mountain ranges. Because across the west coast of Canada, British Columbia, places like that, you get this sort of event happening, wherein the pink and the red parts were a separate plate colliding with the Canadian plate, colliding with that shield, creating all of these mountain ranges that are shown as set there. Of course, the Aleutian Islands at the very top would be ocean, and down below around California, Oregon area is ocean continent. So this map provides all three different examples of mountain building that we've discussed in one nice little pretty picture. And we're going to have lots of very scenic pictures of this type of microcontinent collision event happening here. Glacier National Park in Montana, the Grand Tetons in Wyoming, Rocky Mountains, of course, would be an example of this. And here we can see a picture of how the Canadian Rockies were formed. This crust that's kind of shoved underneath another crust. I mean, you could imagine sort of, I guess if we want to continue with the deck of cards analogy, you're taking a clump of cards and you're shoving them into some others and they're going to buckle up, right? That's what happened here to create these mountains in the way that they've been created. Banff National Park in Alberta, Canada. And when you look at these mountains, I keep stressing this, the Alaska Range, Denali, you're not going to see a difference necessarily in the mountain itself, but having understanding the outline geology provides you with a understanding of how this game is played and how these mountains were created in the way they were created. So let's talk about the difference between a microcontinent collision and a true continent collision. Alpine type mountains happen when you have a suture, a zone where two continents collide and, well, weld together. You get slivers of ocean lithosphere in that, few volcanic rocks, but lots and lots of deformation of thick sequences of sedimentary rocks, fold and thrust belts, and lots of high-grade metamorphic material there, gneisses and schists. This happens, again, because you have two things that don't budge running into each other hard, separating from the microcontinent, this is, again, continent, going at it. The best known and arguably one of the most recent examples of this type of collision would be the Himalayan mountain range, which only started growing about 50 million years ago. In this graphic here, we can see an example of how this happened. The Indian continent, the Indian, plate, I should say, consisting of continental crust, shoved into the continent of Asia, squishing all of that ocean crust in between up together, forming the Himalayas. The Indian subcontinent literally wedged itself into Asia, and the resulting buckling created the Himalayas. If you, I don't know if you're aware, but the Himalayas actually has oceanic crust near the top. There's fossilized seashells and things like that. And those were brought up by this collision event. And it's cool if you look at India, if you dragged it down, you would actually see the scraping that the plate went as it cut through the oceanic crust. Here, a picture showing the direction of India, the Tibet Plateau, pushing to the east and southeast, away from that, being displaced by the Indian subcontinent, smashing into it. Of course, Mount Everest, the tallest mountain in the world, 29,029 feet above sea level, exists in the Himalayas. Massive, massive mountain range. Very, very fresh, very, very new. And on top of all these mountains, seashells. Of course, the Himalayas is not the only example of this sort of mountain making event, this sort of orogenic. The Andes Mountains, my bad, the Appalachian Mountains in the United States also were built in this manner. If we look at these cartoons here, we can see the formation of the Appalachian Mountains, when North America and Africa were driving together about 600 million years ago, closing an ocean basin. At some point, about 450 million years ago, an orogenetic event started to occur when North America ran into the tectonic volcanic arc there. Along with that, the microcontinent of Avalonia is being shoved together. Eventually, Avalonia itself also runs into North America and its continent, creating this gigantic multi-continent cluster of the Akkadian orogeny. Africa eventually slams in about 250, 300 million years ago, buckling up all this already produced orogeny, creating what we now call the Appalachian Mountains. And then after some time, this process reversed. The Atlantic started to form between them, and what was left over was the Appalachian Mountains. Very, very old, again, compared to some things like the Himalayas, very, very old mountain range. Here are some pictures of the Appalachian mountain ranges, and these will look different from the previous images of mountains we've shown in the past, but that's not to do with how they were formed, as we've talked about with our erosion conversations. It's to do with their age and their eroding down. These mountain ranges are not very peaked, not very sharp compared to, let's say, the Himalayas, even though they were both formed under similar circumstances. The Earth, as we've been talking about, is very much a varied topography. Lots of different highs and lows throughout. Why is that? Isostasy, sorry, I can't say that word very well, defines that explanation. The idea behind isostasy, I think I did that right, is that less dense crust floats on top of denser rock of the mantle. This isostasy, that's a tough one, or the floating crust, is gravitationally balanced within the mantle. Again, what does that mean? Well, if we float a bunch of different blocks, as pictured here, in water, even though some blocks are a lot larger than others, most of that's going to be down below, this iceberg effect. So that a block twice the size of a smaller block will not necessarily be much drastically above the water than the other blocks below. Since this crust, this heavy crust, essentially floats within the mantle, the more weight you add, the more it sinks, and the more weight you remove, the more it rises. This crustal rebound is occurring in Canada's Hudson Bay region, following the melting of the ice sheets in that region. And this process pushes up and down the crust of the Earth, causing all these differences. When you stack mountains on top via some sort of, any of these orogenic vents that we've talked about so far, this causes all that to shrink down, causing a buckling in the mantle. So when you have this compressional stress that we've talked about shoving together a mountain range, this compressional mountains are young, and they're composed of thick, low-density crustal rocks that float, as shown here below, on that denser mantle. The mantle flows away from this dense down-pushing of the rock. As you erode the mountain slowly and surely, the isostatic uplift pushes back up. The mantle flows back towards this depression, resulting in, eventually, erosion uplift, returning the mountain range to a more normal thickness of crust. So, that was chapter, 11? Yeah, chapter 11, mountain building. I hope you enjoyed it. Please leave some comments down below. Love to have that conversation with you. I guess it's a YouTube video, so I'll say like, share, and subscribe, but I really don't care, right? This is for class. And, yeah, see you in the next chapter.